Yes, this is the 34th lecture and we are going to talk about small signal models and small signal amplifiers. The amplifiers that we have discussed in the last few lectures, namely power amplifiers, they basically use very large driving signals. They are large signal amplifiers, and that is why we had to bother about the placement of the Q point and the maximum voltage and current swings, because the objective there was to obtain as much power as you can from the given amplifier. In a small signal amplifier, that is not the consideration. The consideration is the faithfulness or the fidelity of the amplifier. That is, whatever waveform you put at the input, the same waveform should arise at the output also. The object is either voltage amplification or current amplification, but not both. We do not want power from small signal amplifiers. What we want is large voltages or large currents. So, it is not important, the Q point placement is not as important as in power amplifier. In a power amplifier, you can tolerate a certain amount of distortion. In fact, a certain amount of distortion is a fact of life. In a small signal amplifier, where fidelity or faithfulness is more important, you cannot do that. We have already introduced the small signal model in the case of a diode. If you recall, if we have a diode which is driven by a battery in series with, let us say, an AC source of value small v, let us say this is V sub d, this is small v sub small d. That is, if the diode is being driven by a DC in series with a very small amount of AC, then the Q point is obtained first. The Q point is obtained by drawing the characteristics and then ignoring the signal. That is, you find out the point at which V is equal to Vd, then this current capital I sub capital D, this determines the Q point, the operating point, and on this operating point you superimpose a small signal. Let us say if this is AC, then maybe the diode voltage can vary between these two limits, the limits drawn by the red lines. All right. Maybe the diode voltage varies like this, superimposed on a large DC, that is a small voltage small v, and then the current through the diode shall also be sinusoidal and it will flow like this. All right. If you wish to find out this current I in relation to this voltage V, then you know that you can work in terms of the slope of this line at the Q point. In other words, you can define an AC resistance small r AC as equal to small v divided by small I, which obviously is delta Vd over delta Id, incremental resistances. And if it is implied that the diode is sitting at this Q point, then given a signal, you can always find the current I, the signal current I, as V by R AC. In other words, the whole diode, the whole circuit can then be replaced by a simple resistance R AC and a voltage V. We forget about the DC part. All right. This is called a small signal model of the diode. All right. It is being implied that the diode is sitting at a Q point such that it always conducts. For all values of small v, it conducts. What I am doing basically is to invoke linearity. We are making a linear equivalent circuit where DC and AC can be superimposed to get the total current. The DC resistance here, for example, RDC is equal to RAC. It is simply equal to V by capital I, which is quite different. V by capital I is quite different from RAC. All right. DC resistance and AC resistance are quite different from each other. For a diode, for example, you know that the current is given by Is e to the power q v by kt minus 1, and from this you can find out di dv by differentiation, and if you do a bit of algebra then it simply comes out as q by kt I plus Is. If you actually differentiate, you can put it in this form, which is approximately equal to qi by kt. All right. So that RAC for the diode, will be given by kt by q divided by capital I, where capital I is the DC current, DC Q point current of the diode, and kt by q at room temperature, you know, this is 25 millivolts. So this will be 0.025 divided by capital I, and this is an important relationship which we shall be utilizing in transistors also. That is, for a junction diode, for a junction PN junction, the dynamic resistance or the AC resistance is simply given by 0.025 divided by the DC current in the diode. All right. It is related to DC because we have found out that the slope of the current voltage characteristic depends on the current, depends on the DC current. All right. This relation we shall be utilizing in the case of a transistor also. Now let us look at a transistor, and for for being specific, let us consider a common emitter transistor. Well, you know, we have to use DC, we have to use a supply, power supply VCC, we have to use resistances to bias the transistor properly, and you know we have to determine a Q point at the middle of the load line to make maximum possible swing and all that. Now for maximum linearity also, the characteristics are maximally linear near the middle of the characteristic. At the saturation point or at the end they become curved. So let us say we have a Q point. Now we want to operate around this Q point. We want to operate around this Q point. That is, at this Q point there is certain value of IB, base current. We want to superimpose an alternating current on this and find out what is the corresponding change in the collector current. And we have seen that there is current amplification. All right. So let us say we enclose this within a box. All right, and we have three terminals: the collector, the emitter, and the base. And you see, this is a 3-terminal network or a 2-port network, which can be characterized in various different ways. This characterization is a small signal characterization. In other words, if we are talking of, let us say, the voltage between this point and this point, then the total voltage is small v subscript capital B capital E. This notation I have explained earlier. Let me repeat. The total voltage between base and emitter is small v subscript capital B capital E, and this is a sum of a DC and an AC, DC and an incremental value. The DC value we shall say VBE, capital V sub capital B capital E, plus small v subscript small b small e. All right. This is the way we are going to represent every quantity. The collector current, for example, the total collector current would be I sub C, capital C. This is equal to capital I sub capital C. This is the DC value, plus the incremental value, which you shall represent by small I subscript small c. This is true for all such currents and voltages. The problem now, we know how to bias it. We know how to put the transistor at a particular Q point. We know how to choose the resistors. We know how to stabilize the bias point. The next question is, if you are concerned with small signals, signals which do not drive the transistor to its limits, all right, that is, maximum dissipation is not called for. How do we characterize the transistor? Is there a simple way of doing it? Yes. We treat the transistor as a linear device, all right. For small signal purposes it is absolutely linear, and therefore DC and AC quantities can be divorced from each other. And therefore we recall, what we do is we relate the voltages VBE, I sub small b that is the current going into the base, this is the signal current, then VCE, that is the voltage from collector to emitter, the small signal voltage, and I sub C as the 2-port variables. There are 2 voltages and 2 currents, and you know that any 2-port can be characterized in 6 different ways. I repeat, this characterization that we are talking of for the transistor is for incremental quantities only, small signals only. We are divorcing DC from the picture altogether. Is that clear? Okay. If we do that, then you see any 2-port device, which has 3 terminals. Well, we say this is V1 I1 in general, V2 I2. You know that we always use currents going in, V2 I2, and you know that these can be characterized in 6 different ways. If we take V1 and V2 as dependent variables and I1 and I2 as independent variables, then the parameters are the so called Z parameters or open circuit impedance parameters. On the other hand, if I take I1 I2 as the dependent variables and V1 V2 as the independent variables, then the parameters that come into effect are the short circuit admittance parameters or small y parameters. There is a third way which has been found very effective for transistors, and these are the hybrid parameters. That is, your dependent parameters are V1 and I2. Dependent parameters is a combination of one voltage and one current. The input voltage V1 and the output current I2. These are expressed in terms of I1 and V2. I1 and V2 are made the independent variables, and naturally the parameters shall no longer be impedance or admittance, they will be a combination. Is that clear? And this is why they are called hybrid. One of them is an impedance, one is an admittance, and the other 2, as you will see, are dimensionless, and therefore they are represented by the H matrix. H stands for hybrid. All right. It is always the input voltage output current V1 I2 expressed in terms of I1 and V2. It's the reverse way around. All right. If we expand this relation, let me rewrite. V1 I2 is the H parameter, I1 V2, and these parameters are named in the same manner. That means we call H11, H12, first row first column is H11, first row second column H12, second row first column H21 and H22, and these are called hybrid parameters. Hybrid, HYBRID. You can see very clearly that H11, for example, how would you define H11? H11 is V1 divided by I1 with V2 equal to 0. All right. If I write this specifically, H11 I1 plus H12 V2, all right, I2 equal to H21 I1 plus H22 V2, then you notice that H11 is simply V1 by I1 with V2 equal to 0, which means that this is an H11 has the dimension of impedance. Similarly, you can see that H22 is an admittance, whereas H12 is V1 by V2 with I1 equal to 0, and therefore H12 is dimensionless, it is a voltage ratio, and H21 is a current ratio and it is dimensionless, and therefore these are called hybrid parameters. In terms of an equivalent circuit, you see that we can represent these relations. What are the relations? V1 equal to H11 I1 plus H12 V2, and I2 equal to H21 I1 plus H22 V2. we can represent this in a very simple manner as a 2 port. This voltage is V1 and this current is I1, this voltage is V2 and this current is I2, and if you notice V1 is H11 I1 and therefore I shall have a resistance here or impedance which has a value of H11. Let us talk of resistive elements to start with. V1 is equal to H11 I1 plus we want a coupled term, coupled. V1 is now coupled to V2, the other port voltage, through a term H1 to V2, and the simplest way is have a voltage generator here whose value is H1 to V2. What would you call this voltage generator? It is a dependent generator. Its voltage depends on V2 and therefore this is a controlled source or dependent voltage source. In a similar manner, I2 has 2 components. One is H2 to V2, which means that this is V2, which means that I2 has 2 components. One flows through a resistance of value 1 over H22, not H22, 1 over H22, so that H22 is its admittance. So V2 H22 is the current and the other current is H21 I1, once again can be represented by current generator, a dependent current generator, a current controlled current source. This is H21 I1. All right. Now, in a transistor, if the terminal 1 is a base, terminal 2 is a collector and the common terminal is an emitter, this is emitter, then you see V1 is nothing but VBE, all right. V1 is nothing but VBE. H11, what is H11 then? It is the dynamic resistance of the forward biased emitter base junction. Between base and emitter there is a junction. So H11 is the resistance of the forward biased emitter base junction. So H11 is represented as R pi. The subscript pi shall be clear a little later. H12 is usually a very small quantity, 10 to the minus 3 is a typical value and therefore we usually ignore this. All right, H12 is usually ignored. Similarly, H22 is usually a very large quantity, H22 is a very small quantity, so that this resistance is very large and therefore this resistance also, yes, should be put equal to infinity, that is this resistance one can do without, all right. And H21, you can recognize what H21 is. What is I1? I1 is simply IB, the base current, and therefore this I1 is IB. Then what is H21? It must be beta. H21 is beta, I1 is IB and I2 is I sub small c, the collector current, and V2 shall then be equal to VCE. All right. With these simplifications, therefore, we get a simplified equivalent circuit of the common emitter transistor. Note that these simplifications have been done under 2 conditions. One is that this controlled source can be ignored because H12 is a small quantity. This resistance can be ignored because H22 is a small quantity. All right, H12 and H22 both tend to 0. It is only under that condition that we have in the equivalent circuit just one resistance and one controlled current source, all right, beta IB, and therefore my equivalent circuit simply becomes R pi. This is VBE, this current is I sub B, and we have beta I sub b. That is it. This is the collector, this is the base, and this is the emitter. This is the equivalent circuit of the common emitter transistor. Well, you can find out what R pi is. R pi, as I said, is the dynamic resistance of the forward biased diode, and therefore R pi shall be, it is clear, it is VBE divided by IB, all right, and you know what this is. This is, as we had already found out, 0.025 divided by capital I subscript capital B. It is the DC value of the base current. Usually this is written in terms of the collector current. This relationship is written in terms of collector current. So, if I put I sub C here, naturally I should multiply this by beta, beta times 0.025 divided by I sub C. This is the value of R pi, and you see R pi depends on the Q point. R pi depends on the collector current at the Q point, all right. Beta, of course, is the beta is H21 or beta. Now, this beta is slightly different from DC beta. This beta is AC beta. This beta is I sub C. This beta is I sub C divided by I sub E. I am sorry, I sub B. That is, it is the ratio of incremental collector current to incremental base current, all right, and this beta is slightly different from the DC beta, which is I sub capital C divided by I sub capital B, for very obvious reasons. It depends on a slope, the other one depends on the total quantities. Nevertheless, the values are very close to each other, all right. Now, I want to represent this equivalent circuit. It is so important that one has to draw it again and again. I want to represent this equivalent circuit in a slightly different form. I sub B, V sub BE, and V sub CE. This current generator is beta I sub B, and I can write this as beta I sub B can be written as VBE divided by R pi, all right, and therefore I can write this as, what would be the dimension of beta by R pi? Conductance, and therefore I represent it by GM. GM stands for transconductance or transfer conductance. It is transfer because, well, I represent this as GM VBE. Okay, this is a current generator which can be represented by GM VBE. The current here depends on the voltage here, and therefore it is a transfer conductance or transconductance. The value of GM, as you can see, is beta by R pi, and if you recall what R pi was, you simply see that this is I sub C divided by 0.025, all right, and the unit is mho. 1 by 0.025 is exactly 40, and therefore this is an extremely nice relation, 40 times I sub C mho, and this is what is used in practice rather than R pi, rather than beta. It is convenient to use GM because it is very easy to calculate GM. It is very easy to remember that GM is simply 40 times I sub C. For example, if I sub C is 2 milliamperes, then GM would be 0.8 mho. Is that okay? 0.8 mho. 80? No, it is 0.08. 0.08 mho. All right. So, we shall use either of these two circuits. One is called the R pi beta circuit, beta IB, this is IB, equivalent circuit of the transistor, or the same circuit represented like this. We shall use this as small v, it is VBE actually, and we shall represent this as GMV. This is the other circuit, all right. They are absolutely equivalent to each other. Suppose now we make an amplifier, the most elementary amplifier, that is we have a let us say Vi, perhaps we can include a source resistance Rs, then of course we have the DC bias, let us say VBB. Is the polarity correct? The base should be positive with respect to the emitter. There is a PNP transistor, and suppose in the collector circuit we have a load RL and the collector biasing supply minus plus, and this is VCC. This is our elementary amplifier, and we want to know what is the signal voltage across RL. This is an elementary amplifier. We wish to know what is the gain of this circuit, what is the amplification of this circuit. All right. What we will do is we will replace this transistor and its associated DC biases by the incremental equivalent circuit, and then calculate the ratio of the signal at the output to the signal at the input. And as you see, this would be extremely easy. We do not have to refer to the characteristic curves at all. All right. We shall do simply in terms of the equivalent circuit. What I do is I divorce all the DC quantities Vi, Rs, then between the emitter, between the base and the emitter, I have simply R pi, and this voltage I call V. All right. Then I have GMV at the collector. What else do I have? Simply RL. All right, the load RL, and this would be my output voltage V0. You can easily see that the output voltage V0 is simply minus GM V times RL. Why is the negative sign? Because the current flows like this. The voltage polarity is positive up and negative down. All right. So if I can find what V is, if I can relate V to Vi, then I shall know what is the ratio of the output voltage to the input voltage. And you can see that small v is nothing but R pi divided by Rs plus R pi times Vi. So if I substitute this value of V in this relation, then I get V0. Let me use a different color. V0 I get equal to minus Gm R pi RL divided by Rs plus R pi times Vi. Therefore, the gain of this circuit or the amplification of the circuit, which is given by V0 by Vi, will be simply equal to V0 by Vi. The gain of the circuit would be equal to minus Gm R pi RL divided by Rs plus R pi. What is Gm R pi? Beta, and therefore this is minus beta RL divided by Rs plus R pi. What is the significance of the negative sign here? Phase shift. The output voltage is out of phase with the input voltage, and this I have explained again and again, that an increase in the input voltage causes an increase in the collector current, and an increase in the collector current leads to a reduced value of collector voltage VCE, and therefore there is a phase change, and this is reflected in the minus sign, and this ratio has to be dimensionless because it is a ratio of two voltages. Typically, for example, you may have a beta equal to 100, RL can be, let us say, 1K, Rs we would like it to be as small as possible, let us say this is 0.5 K, and R pi may be of the order of, let us say, 1.5 K. All right. Then you see that the gain, which is usually represented by the letter A standing for amplification, for this typical circuit it is minus 50 divided by 2, that is equal to minus 25. Oh, beta is 100, okay. So, this would be minus 50. In other words, if you put 1 millivolt at the input, 1 millivolt peak, then you get at the output a voltage which is 50 millivolt peak, alright. And if you use a higher beta transistor or you can reduce RS, you can get a higher gain. The gain can be increased to, there is an upper limit, but it can be increased to an useful value. For example, you have a signal from maybe a process instrumentation of the order of, let us say, microvolt, which cannot be read by a meter, alright. A microvolt meter is a very costly equipment. So, what you do is you put an inexpensive amplifier in between and raise it to 100 microvolt, alright. Then you read 100 microvolt is how many millivolts? 0.1. There are millivolt meters, fractional millivolt meters and so on. Or maybe you want to use this to drive a power amplifier. For example, in the public address system, the microphone amplifier, the microphone signal does not go directly to a power amplifier. There is something called a pre-amplifier. What a pre-amplifier does is simply to raise the voltage level so that it can drive the power amplifier stage to its complete capability, alright. So, that is the basic idea of amplification. Now, let us go back to this R pi beta model, R pi and let us say GMV model, and see, as I said, this is a very simple model. There are some modifications needed to take care of elements, to take care of performance at high frequencies in particular. And this is a very gross model. To sharpen the model, we require several modifications. One is, if you recall the structure, if it is an NPN transistor, NPN, there is a connection here which is the emitter, there is a connection here which is the collector, there is a connection here which is the base. The base, as you see, is a thin long region, and between the actual contact of base and the base emitter junction or base collector junction, there is a certain amount of resistance which sometimes plays havoc, and this resistance is called the base spreading resistance, and it is denoted by Rx. Rx, this is called the base spreading resistance. This happens because of the thin and long nature of the base. The base spreading resistance, a typical value is of the order of 100 ohm. A typical value for R pi, that is a dynamic resistance of a base emitter junction, of the order of, typical value is about a K. So, R pi is usually one order of magnitude higher than Rx, and in most of our analysis we shall neglect Rx. Alright. Between the base and the collector, where there is a junction. What kind of biasing is there in this junction? Reverse biasing, alright, and therefore in a reverse bias junction, as you know, there is a separation of charge, alright. This separation with reverse bias increases, and therefore this acts as a capacitor, which means that between these 2 points we should have a capacitor, and this capacitor is given the symbol C mu, the capacitor between the base and the collector, C mu. Unfortunately, it is not a pure capacitor. There is also a conduction current, and this conduction current is usually represented by a resistance in parallel with C mu, and it is called R mu. Alright, R mu. R mu is usually very large, of the order of several megs, and in usual circuit considerations, R mu can be ignored compared to 1 by omega C mu. At high frequencies, when C mu comes into consideration, it dominates. that is 1 by omega c mu is much smaller compared to r mu. So, r mu can usually be ignored, alright. In addition, you know the base emitter junction also contributes to a capacitor, alright. The base emitter junction also, there is still a separation of charges. So, there is a capacitance here also, and this capacitance is called C pi. The capacitance in parallel with R pi is called C pi, alright. Between the collector and the emitter, if you connect a battery, a small current does flow, and this current is taken care of by a resistance R0. All that I show in red here are not desirable, they are all undesirable elements, they are called parasitic elements. Unfortunately, however, parasites are facts of life and one has to take care of them, alright, whether in public or in politics or in electronic circuits, parasites are facts of life. Okay. Now, so in our usual amplifier analysis at, yes.
So in this case, what is V?
Oh, what is V? V is this voltage. I forgot to mention this. V is the voltage across R pi. V is the voltage across R pi. Yes. This is why we prefer this model, not only because GM is very easily calculated, 40 times IC, but also because it does not take account of the current division. You see, the IB comes here, it divides into 1 part, 2 part, 3 and 4 parts. We don't take care of the current, we take care of the voltage. And GMV, this is the most accepted, the most general model of a common emitter transistor. And you see, the model looks like a pie. You see, it looks like a pie, and therefore it is called a hybrid pi model of the transistor. Hybrid pi, it originates from the hybrid parameters H11, H12, H21, H22. We first went through a simplification and then brought back all the parasites, and it looks like a pi, and therefore it is called a hybrid pi model. For the purpose of this course and for the rest of the lectures, we shall be satisfied with a simplified model. We shall ignore Rx, and therefore what we will have is an R pi in parallel with a C pi, and this voltage is V. Then we shall have a current generator GMV, and very unfortunate, this capacitor C mu is usually a very small capacitor of the order of 3 puffs, that is 3 times 10 to the minus 12 farad. C pi is of the order of 100 puffs, about 30 to 40 times larger. Even then, because of this current control, because of this voltage controlled current source, C pi can cause havoc. C mu can reflect at the input and can even swamp C pi. That means effective value of C mu reflected across the input can be much larger than C pi, and therefore C mu has to be considered in practice. We take an example to illustrate the usefulness of the model, and this example is the so called Darlington amplifier. Darlington, it is a name, Darlington stage as it is called. What is done is the following: you have a common emitter, stage, not common emitter, common collector. The collector is connected directly to VCC, and you apply an RS and a VS here. This is the source. I am not showing the DC biasing, I am only showing the incremental quantities or the signal quantities, alright. This emitter, instead of going to ground, goes to the base of another transistor, alright. and the collector of which is connected to the same VCC. Okay. Then this goes to ground through a resistance R sub E, and it is across R sub E that you take the output voltage V0. I am not showing the DC quantities, I am showing only AC quantities. All right. Across this you take V0. Now you see what in effect the circuit is, that instead of a single transistor emitter follower, as I had introduced last time in the 33rd lecture, a single transistor is now replaced by two transistors. The emitter current of one becomes the base current of the other, and you can expect that there would be a very large current amplification. The current amplification would be very grossly, you can see that the emitter current would be beta plus 1 times the base current, and this emitter current will be beta plus 1 times this base current, and therefore the current amplification should be beta 1 plus 1 times beta 2 plus 1. If this transistor you call Q1 and this you call as Q2, this is what will happen, and this is what indeed happens. You see, if your beta 1 is 100, then approximately this is 10 to the power 4. A single transistor with a beta of 10 to the power 4 cannot be fabricated, and therefore this is a way to have a high beta equivalent of a high beta transistor. If I draw the equivalent circuit, then I will leave the rest of the analysis to you. If I draw the equivalent circuit, I have Vs in series with Rs, then for Q1 I have R pi 1, all right, and I have beta 1. If this current is I sub B1, I have beta 1 IB1. Where does this go? This point is the collector, this point, this is the collector, and the collector is connected to VCC, therefore it is equivalent to going it to ground, and therefore this goes to ground. Now this current whatever the current is, goes to the second transistor B2, and we have R pi 2, so this current is IB2, and then we have beta 2 IB2, the two come together. Where does this go? Ground once again, and then this current now flows through R sub E, and this is the circuit V0. This is the equivalent circuit, and you can very easily analyze this just by looking, just by common sense. You see that IB2 is simply IB1 times beta 1 plus 1, and therefore this current is IB2 times beta 2 plus 1, and therefore this is beta 1 plus 1 beta 2 plus 1 IB1. This current is this current generator plus the current here, all right. So indeed you see that if I call this current as I0, the current through the load, then I0 and current through the source is IB1, and therefore the current amplification AI is simply equal to beta 1 plus 1 beta 2 plus 1, as we had indicated from common sense, all right. If you want to calculate V0 by Vs, that is the voltage gain, AV will be equal to V0 by Vs. What is your guess? What should be the voltage gain? Can the voltage gain be greater than 1? No, it would be slightly less than 1 in fact, all right. If you look at this circuit, you see this voltage minus VBE1 minus VBE2 is this voltage, and for AC this voltage should be exactly equal to the AC of this voltage, which means that the voltage gain should be equal to 1, but because of RS the voltage gain is slightly less than 1, because what you apply here is not Vs, it is slightly less than 1. The advantage however, if you recall, another advantage besides the current gain is that it gives a very high input impedance. The input impedance is very high. You can derive what the input impedance is, that is, find out this voltage from here to ground and divide by IB1. That will give you the input impedance. Input impedance is very high, and this is called a Darlington stage, a very popular stage in integrated circuits. In integrated circuits, all input stages are Darlington stages, so that you get the benefit of a very high input impedance. All right, this is the model that we are now going to utilize to analyze small signal amplifiers, and we shall introduce a couple of terms in this connection and then leave it for tomorrow's class. A small signal amplifier usually is classified according to the coupling that one makes from one stage to another. Stage 1 to stage 2, when one transistor is not enough for gain, you may have to use multiple transistors, and the way stage 1 is connected to stage 2 is technically called coupling, which is obvious. It could be stage 1 to stage 2 or stage 1 to the load, for example. Okay? Usually the load is to be coupled, load is to be decoupled from DC, and therefore use a capacitor and then the load. Okay? Maybe this is RL and this is RC. This coupling, stage 2 can be simply the load or can be another stage of amplifier. Okay? For example, input stage also, input connection, you know that you have a biasing circuit like this, and how do you connect the input? Through a capacitor. All right. So coupling to the transistor either at the load side or at the input side, depending on what kind of coupling you employ, we call it by different names. For example, this is called RC coupling, resistance capacitance coupling. On the other hand, you have seen in power amplifiers, you can couple to the load through a transformer. This is called a transformer coupled amplifier. All right, and a simple small signal amplifier that we shall analyze in great details next time is the most familiar circuit in which there is one transistor Q1, it is coupled to the load through a capacitor CRL, the base is biased through R1 and R2, this is called the self biasing circuit, and the input is coupled through, let us say, RS and Vs. Our purpose will be to determine the voltage V0 in terms of Vs, and that will determine the gain. The capacitors, I have made a mistake in this. This resistance Re has to be bypassed by means of a capacitor which you shall call Ce. There are three capacitors. The first capacitor, you see these two capacitors are coupling capacitors. This capacitor couples the source to the transistor. This capacitor couples the load to the transistor. This is called CC1, coupling capacitor 1, and this is called CC2. This capacitor is called CE because it decouples the AC from RE. No AC is dropped across RE. AC passes through CE. Next time we shall see the effect of these three capacitors and also the capacitors C pi in the transistor model and C mu. by taking a specific circuit and analyzing it. Thank you.